back to the afternoon session of the differential geometry. And our first talk, it is my pleasure to introduce Professor Bruce Kleiner from New York University, and he will present us a talk on Ricci flow and diffeomorphism groups of three manifolds. Let's welcome.
Let's see. So, right. So when I get to the new results, this will be joint work with Richard Bemmler. I guess before I get started, I would say that the topic here is kind of a mixture of topology, geometry, and analysis. The problem that motivates this is really a problem it's an old problem in topology. And then the plan is to reformulate that using some geometry, but the actual solution will involve some geometric analysis or geometric PDE. Okay? And so the plan for the talk is I'll begin with the topological motivation, the origins of the question, and then kind of move toward the geometry. And then the middle part, most of the talk, the last part of the talk will be about geometric PDE. But then I'll circle back to the topology and in the very last part of the talk. Okay. All right. So let's set notation. So X is going to be say X is a compact connected smooth manifold, and then the object of that doesn't do that again. So we're going to be interested in the diffeomorphism group of the manifold. So this is just, right, this is a set of smooth diffeomorphisms, and I'll put the C infinity topology on that. Okay, so that means the sequence of diffeos converges to some limit if it converges uniformly, along with the kth derivatives for every k. Okay? So in this talk, essentially all the results will be unchanged if you replace the C infinity topology with the C1 topology. Now inside diff, you can look at the identity component, the connected component of the identity element. It's not hard to see that this is path connected, and therefore something lies in that identity component if there's a path of diffeomorphisms going to the identity. In other words, if it's isotopic to the identity. Okay. And all right. So the basic motivating question here is, what can we say? What can we say about the topology of diff-X? So there are various motivations. I guess as a fundamental motivation, diff-X is just the symmetry group of the manifold. We like to understand symmetry groups of structures. From another point of view, right, if you're a basic project in geometric topology is to classify manifolds up to diffeomorphism. If you know that X and Y are diffeomorphic, then you may want to classify the ways of the diffeomorphisms from one to the other, which boils down to diff-X. I mean, another point of view is in terms of the mapping class group. So the mapping class group of X is just the quotient of diff-X by the identity component, or in other language, it's the group of isotopy classes of diffeomorphisms. And so, of course, this has been very heavily studied. In the case of surfaces, it shows up all over the place. So you can think of diff as kind of a refinement of the mapping class group. And another motivation for looking at this question comes from thinking about fiber bundles where the fiber is diffeomorphic to X, but there's the structure group is diff-X. So you build a bundle where the fibers are copies of X, but there's no finer geometric structure. Then that leads you to understand want to understand this question. Okay. So all right. So what I'm going to do is to start looking at this question, starting from low dimensions and going up. Mostly won't get much further than 3. Okay. But let's start with dimension 1. So if we're looking at connected one manifold, it's a circle. So you can think of the circle as the unit circle in the plane, and the orthogonal group O2 acts on the circle. And so you can see O2 as a subgroup of the diffeomorphism group, right? And it's not hard to see that subgroup is a deformation retract of the full diffeomorphism group, right? So it carries the topology of diff S1. This is not hard to prove. If you've never seen it before and you spend 5 minutes, you'll come up with a proof a nice proof would be to take a diffeomorphism and use that as an initial condition for the heat equation and look at the solution, and that will converge to an isometry, an element of O2. Okay. So let's move up a dimension. We move up a dimension. We think of the unit two sphere in R3. You have the corresponding statement right here. O3 you can think of as a group of a nice Lie group of diffeomorphisms sitting inside the diffeomorphism group, and then the claim is that that the inclusion of O3 into diff is a homotopy equivalence. Okay, so that nice Lie group carries the topology of diff S2, right? So so unlike the result for the circle, all known proofs of this, I mean, there are many different ways of proving this fact, but all of them use some non-trivial ingredient. It's not just an element exercise. Okay. So I mentioned, right, the version for homeos was done by Knaser long before in 26. And so what I want to do next is give a proof of this, or outline a proof of this, which is different from Smale's original proof, but it will serve as a model for what we do later. Okay. So, okay, a little notation. So now met X will be just the set of smooth Riemannian metrics with the C infinity topology. And then inside there, right, you can look at the metrics for any constant C, for any real number C. You can look at the Riemannian metrics with constant sectional curvature C. Okay? So at every point, for every two plane in the tangent space at that point, the sectional curvature is equal to C. All right? Of course, it might be empty. For a given manifold. All right, so let's look at this lemma. So the lemma is that this assertion that we're interested in, so the assertion in Smale's theorem that O3, the inclusion of O3 and diff S2 is a homotopy equivalence, that's equivalent to showing that it's equivalent to the assertion that the space of curvature 1 metrics on the two sphere is a contractible space. Okay, so it isn't saying that the inclusion is a homotopy equivalence. All this lemma will do is trade the assertion we're interested in, which is a statement about diffeomorphisms, for some statement about a space of metrics. Okay, we'll look at that statement. So how does this work? Boy, this is ticklish. Okay, so the first step is to notice that if you have a diffeomorphism of the two sphere and you're a Riemannian metric, you can use that diffeomorphism to push forward the metric. Okay? So if the metric you start with is a curvature 1 metric, the push forward also is a curvature 1 metric. So therefore we get an action of diff S2 on the curvature 1 metrics. And right, if a metric on the two sphere has curvature 1, it's been known since the 19th century that such a metric is isometric to the standard metric, right? And that means you can push forward the standard metric to that metric, or in other words, this is a transitive action. So now we have a transitive action of a group on some set, which means that we can think of that set as a coset space. It's a coset space of the acting group diff S2 mod the isotropic group of the stabilizer of our favorite element. So let's take the element to be just the standard metric on the two sphere. The diffeomorphisms which stabilize the standard metric on the two sphere, that's just O3. Okay, so now we can think of the curvature 1 metrics as diff S2 mod O3, and we promote we promote this to a fiber bundle. Okay, so there's a little bit of fine print here. I mean, of course, the diffeomorphism group is some kind of infinite dimensional Frechet manifold. If you had a corresponding statement where the group acting were some finite dimensional Lie group, then this would be an exercise in differential manifolds. Okay, but this requires a little bit of work, but it's standard since 1960s. Boy. Okay, so now we have this fibration, and so just from the exact sequence of the fibration, so the inclusion of the fiber into the total space gives you an isomorphism on homotopy groups if and only if the base is contractible. Okay. So all right. So let's focus on this second condition, showing that the space of curvature 1 metrics is contractible. So if we're going to do that, then first of all, we want to have some way of deforming metrics, right? We're trying to prove that space of metrics is contractible. So this leads to Ricci flow, right? So that's the idea of deforming a metric according to its curvature. So this was introduced by Hamilton. So if you have a smooth family of metrics, say GT defined for t in some time interval, okay? It's a Ricci flow if it satisfies this equation, right? Time derivative is minus twice the Ricci. And Hamilton showed that this has a unique solution for short time on a compact manifold, right? So if you have, say, X a compact smooth manifold, you give yourself some metric H, right? Then you can solve this equation uniquely for short time and then prolong that to a maximal time interval, okay? So you have this unique solution. I'm going to use the notation here from 0 up to capital T for the maximal time interval. Okay, and he showed that if the right endpoint here, capital T, is finite, then what's happening is that as you approach this right endpoint, the curvature is blowing up. Okay, so it's often called the blow up time when it's finite, right? So example, you can look at the standard metric on the end sphere. So in that case, the metric at time t for the Ricci flow will be just that metric multiplied by this linearly decreasing function of time, which goes to 0 at 1 over 2 times n minus 1. So that the metric is going to 0, the curvature is blowing up. Okay, this is exactly what's predicted by Hamilton's theorem. Now, in the two-dimensional case, there's a beautiful result of Hamilton and Chow, right? That if you take any Ricci flow in the two-sphere, then in fact, this right endpoint is finite. So it actually blows up in finite time. And the behavior as you approach that capital T is very nice. So what you do, you take the metric, you rescale it. If you rescale it to normalize the area, then this rescaled metric actually converges to a curvature 1 metric as you approach the blow-up time, capital T, okay? So, corollary, right? So it's basically saying you take an arbitrary metric, this gives you a process for deforming it canonically to a curvature 1 metric, and that will tell you that the space of curvature 1 metrics is a deformation retract of the space of metrics, okay? And the space of metrics is contractible because it's a convex subspace of some subset of some linear space. So this is contractible, and you have something which is homotopy equivalent to it, so that's also contractible, okay? So this establishes what we were looking for. So side remark is the same argument shows that the space of positively curved metrics is also a contractible space, just again using Ricci flow. So I want to mention that, right, so this argument used the equivalence between these two assertions here at the top, but you can, there's soft arguments that you can use to prove equivalence to other natural sounding statements. Like, for example, this statement of Smale's theorem is equivalent to the contractibility of the space of embedded circles in the plane. Okay? So think about the space of all embedded circles in the plane. The contractibility of that is an equivalent statement. Or you can look at diff of the disk rel the boundary, okay? And that's, in other words, you look at the group of diffeomorphisms of the disk, which are the identity on the boundary, that's contractible. In fact, that's the assertion that Smale used together with a very clever dynamics argument. Okay. So let's look at some other surfaces. So let's say we're looking at an orientable surface of genus G at least 1. So now let's look at the identity component of that. And so the identity component, there are two cases. So it's contractible if the genus is at least 2. And if the genus is 1, so we're looking at a torus, right? In the torus, you could think of the torus as a group. And then the translations in that torus give you a group of diffeomorphisms. It's like a copy of the torus that's sitting inside diff 0. And that carries the topology, okay? The inclusion of that torus in diff 0 is a homotopy equivalence, okay? Now, if you want to understand the full diffeomorphism group, well, then you look at the quotient, but that's a mapping class group, which has been well understood for a long time, okay? So these guys proved this using conformal, well, there's one proof using conformal geometry, and you can also, in the higher genus case, you can give a proof using Ricci flow. And there, for example, in the genus 2 or higher case, you use Ricci flow to deform your metric to something of a constant curvature -1. And I note the same argument will tell you that the space in higher genus, it'll show you that the space of negatively curved metrics is contractible. Okay. So let's go up a dimension to 3 manifolds finally. And the simplest 3 manifold you might look at would be the 3-sphere. And so Smale conjectured in 61 that the corresponding statement is true for the 3-sphere, right? So O4, inclusion of O4 into diff S3 is a homotopy equivalence. And very soon after that, Cerf proved this on the level of pi 0, on the level of path components, meaning if you have a diffeomorphism of S3, then it's isotopic to an isometry. Okay, so that happened soon afterward, but a long time passed before the full conjecture was proven by Hatcher in 1983. So let me just mention, there's by similar reasoning, this Smale conjecture is equivalent to a bunch of other conditions. For example, the space of embedded 2 spheres in R3, that's a contractible space. In fact, that's the assertion that Hatcher used. And it's also equivalent to the contractibility of the curvature 1 metrics or the contractibility of the diffeomorphisms fixing the boundary. Okay. So at the time, since Hatcher's proved his theorem, I would say that there are not a lot of people who understand his proof well, and there's certainly people have wondered if there are other proofs or other approaches to it. Maybe if you're an analyst, you wonder if you can somehow use tools from analysis to approach this, and I'll come back to that. Okay. So let's move on to look at some other 3 manifolds. So let's say, again, X is compact connected, 3 manifold, I think. So let's suppose we have a metric GX, which is a curvature 1 metric on X. All right, this places a very strong restriction on X. You have a curvature 1 metric on your 3 manifold. The universal cover is isometric to S3. So that means X is just the quotient of the 3-sphere by some finite subgroup of O4. Okay, diffeomorphism. So this is really a conjecture about spherical space forms. All right. Now, if you have such a metric, then there's an obvious kind of natural group of diffeomorphisms sitting there, namely the isometry group of this curvature 1 metric. You have this nice symmetric metric. You can look at the isometry group. That's gonna be some Lie group. I do not understand why this is happening. That's gonna be some Lie group that's sitting inside diff. And so the conjecture is, well, that carries the topology of the diffeomorphism group. And right, in the case you have the 3-sphere, the isometry group, just take GX to be the standard metric, and this is just the original Smale conjecture. Okay, so this is a generalized Smale conjecture, which dates from the late 70s. And so, as before, you can relate this to a statement about curvature 1 metrics. So this generalized Smale conjecture is equivalent to the contractibility of this space of curvature 1 metrics. So the first theorem is that the generalized Smale conjecture is true, and we use Ricci flow to prove this. Okay. All right. So previous work. So the analog of Cerf's theorem, that the version of this on the level of paths or connected components. So this was established in different cases over the course of this period from 78 to 91. And then the full conjecture was actually known for some spherical space forms. Okay, so 3-dimensional spherical space forms come in 6 infinite families. Okay, and it was known how to prove the full conjecture for 3 out of the 6. Okay, they're the ones which contain incompressible one-sided Klein bottles, where they have Hagar tori. Okay, and there are 3 more, which are the tetrahedral, octahedral, and icosahedral manifolds. Those are 3 more infinite families for which it was open. Okay, so these proofs the proofs here, the idea was to exploit the existence of this special surface, maybe the one-sided Klein bottle, and somehow the main argument is sort of to reduce to the case where, reduce is not quite the right word, but to the setting where you look at diffeomorphisms which fix that surface, and then you can cut the manifold open along that and appeal to Hatcher's result. Okay. So I note our proof, well, we actually have two proofs. One of those is independent of Hatcher, and it gives a new proof of the original Smale conjecture. Okay, so let's look at other three manifolds. Okay, so let's say we have X, it's closed, orientable, and irreducible. So remember, irreducibility is a sort of a strengthening of being prime. So X is irreducible if whenever you see an embedded two-sphere, it bounds a three-ball on one side or the other. Okay, that excludes non-trivial connected sums. And now X is Haken if it contains an incompressible surface. So that means the following. So you can find an orientable surface N should have non-positive Euler characteristic. So that the inclusion of N into X is a monomorphism on pi 1. Okay. So these were studied since starting in the 60s. The idea is that if you have such a surface, then you cut the manifold open, the pieces you end up with also have incompressible surfaces, and you can keep cutting, and this gives rise to a hierarchy that you can use for induction arguments. Okay, so right, so if you have X Haken, so then the mapping class group by theorem of Waldhausen. So that's the quotient. That's the group of isotropic classes of diffeomorphisms. That's isomorphic to the group of homotopy equivalences of X to itself up to homotopy. Okay, and then now if you want to understand the diff zero, so the connected component of the identity, they show again we're in the Haken case that diff zero is homotopy equivalent to a K torus where K is the rank of the center. Okay. Or equivalently, if you take a metric which is maximally symmetric, then it's going to be isomorphic to homotopy equivalent to the identity component of the isometry group. So think of the example, say a surface of genus 2 cross a circle, right? So there you can think of it, the circle itself is kind of acting, and that will give you a subgroup of the diffeomorphism group. That would be an example where K is equal to 1. All right. So these results actually predated Hatcher's resolution. They were kind of conditional on the positive resolution of the Smale conjecture, which came a few years later. Okay. But so that leaves the non-Haken case. So here we have to use the geometrization Thurston's geometrization conjecture, and using that you can see that the non-Haken cases are these. So they're going to be three manifolds which are modeled on Thurston geometries from this list. I'm not even touching the computer here. Right, so there'll be quotients of the standard three-sphere, hyperbolic three-space, hyperbolic plane cross R, SL2R, uniform cover of SL2R, or nil, so the Heisenberg group. And right, so we already discussed the case of the three-sphere. That's the generalized Smale conjecture. What about the other cases? So the case of non-Haken manifolds X. The other cases, we look at the inclusion of the isometry, the identity component of the isometry group, and the identity component of diff zero. So that the hyperbolic case was treated by Gabay in 2001. And then in 2013, so that takes care of this case. That leaves three more cases. These two cases were done by McCullough and Soma in 2013. And then that left one remaining case, nil, which was not amenable to their methods. And we can cover that using Ricci flow. So this completes the story of irreducible three manifolds. So I want to mention that just very recently, maybe I should stand back so we'll see that we'll do that. There's been major progress on reducible three manifolds that actually is built on all this previous work, and the irreducible case plus a bunch of other ingredients. So this in particular resolved a conjecture of Conceiv's called the finiteness conjecture. Okay, just mentioning in passing what happens in high dimensions. Well, the story kind of collapses in high dimensions. So if you look at the corresponding statement in high dimensions, it's not a homotopy equivalence for any n at least 5. Also, for the homotopy type of diff is not known for any manifold of dimension 4 or higher. That said, there's been major progress in the last few years. Major progress due to Cooper's, based on earlier work by others. So that's very encouraging. Okay, now I want to look at another. So the story here, our approach is to take the question about the structure of diff and relate that to the topology of some space of metrics, right? The space of curvature 1 metrics, say. And so actually there are other cases other situations where you may be interested in understanding the topology of the space of metrics of satisfying some condition, right? And one that's been of longstanding interest is positive scalar curvature. So I want to cover this briefly, right? So let's say Met PSC, that's the space of metrics on X which have positive scalar curvature. It's a consequence of Perelman's work. So this completed the story that with prior work by a number of people. If you have a compacted 3-manifold, it has a metric of positive scalar curvature if and only if it's a connected sum of xi's, which are either spherical space forms or copies of S2 cross S1. Okay, so that's the existence. But once you have one such metric, you can wonder what does the space of solutions to this this curvature condition look like. So Marquez showed that this moduli space, the quotient mod diff, that's path connected. In the case of spherical space forms, it's the space itself is path connected, and so we went from pi 0 to full contractibility. Okay, so for any 3-manifold, the space is either empty or contractible. Okay, in higher dimensions, so there's a very famous work of Hitchin in the 70s showing that the space of metrics with positive scalar curvature can even be disconnected for spheres. Okay, so the behavior, nice behavior, simple behavior in dimension 3, and breaks down in high dimensions, and even the moduli space, when you mod out by diff, that can have infinitely many connected components. Okay. All right. So one last thing here. So there's a very natural question in this space that I want to mention, which is this. So if you have hyperbolic 3-manifold, right, so that means it has a metric with constant curvature -1. Well, then you can look at the space of metrics which have negative sectional curvature. And it's very natural to ask if that's a contractible space. So that's seems very much in this space. The analog in higher dimensions is false by work of Farrell and Antoneda. Okay. So now I want to shift gears and talk about some of the ingredients that go into the proof of the generalized Snell conjecture and say something about the outline. Okay. So let's come back to this setting. So let's say X is a spherical space form. And we want to show, right? We want to show that the space of curvature 1 metrics, or maybe the PSC metrics, are contractible, and we'd like to use Ricci flow, right? It's a very nice outline in the case of the 2-sphere. Okay, so the bad news is that Ricci flow in dimension 3 is much more complicated than Ricci flow in dimension 2. Okay, so for the next segment of the lecture, you can almost put all this discussion on hold. It's going to be a discussion about Ricci flow, and then I'll come back to connect that up with these questions after in a little bit. Okay. So right, so in dimension 3, if you start with the standard metric on the 3-sphere, as I already said, then the Ricci flow with that as initial condition looks like this. It's the metric just scaled by 1 minus 4t. Right, it goes to 0 at time 1 as you approach time 1/4, and the curvature blows up. So that's what we saw before. But if you take something that's not so symmetrical, so if you take a barbell metric, then the Ricci flow gives you a neck pinch singularity. So here, so let's say we have an initial metric, which schematically looks like this. It has two roughly spherical regions and then a neck region in between. So if the neck is not so tight, then under evolution, the Ricci flow will eventually have positive curvature. And then as you approach blow up, the metric becomes asymptotically round. On the other hand, if the neck region is kind of tight, then the positive curvature there will make the neck shrink. As it shrinks, the curvature gets even bigger, and you get this instability, which is the neck pinch. Okay. So what happens is, as you approach, in this case over here, as you approach the blow up time, the metric will actually, it's going to go singular in this neck region, but it will actually have a smooth limit on an open set away from that. Okay. So this is very different behavior from what we saw before. As you go to blow up, there's still some part of the manifold left where the metric makes sense. You have a nice smooth limit. Okay. So this suggests that you might want to try to continue the flow in some way. So this is an idea that was due to Hamilton. He called it Ricci flow surgery. And this was further developed by Perelman. So the cartoon is as follows, right? So you take your initial metric, you flow it until the metric goes singular, or maybe stop just before that. Then you identify the region where the curvature is where the metric is either blown up or the curvature is large. And then you find neck regions on either side here and you cut along the cross-sectional two spheres and throw away the bad part of the manifold and then cap it off. So this is called surgery. Now you have a compact manifold and you can restart the Ricci flow, okay? And then maybe do surgery again and so on. So this is an alternative process. You alternate between Ricci flow and this surgery. So this has spectacular application. So this is what Perelman used to prove the geometrization conjecture. So, which is terrific, right? But you might note that this is kind of an ad hoc construction. It's not a canonical process. It involves a number of choices. This was pointed out by Perelman himself. So he said it's likely that by passing to the limit in this construction, one would get a canonically defined Ricci flow through singularities. But at the moment, I don't have a proof of that. Okay, so he didn't define what he meant by a Ricci flow through singularities, but here's the cartoon. Okay, so you have, as before, you have this initial condition. You flow, a neck pinch starts to form, but somehow you just flow through the neck pinch and you keep going. Okay, so that's somehow the heuristic. So there are several motivations for looking at this. First, you can think of Ricci flow with surgery as a kind of regularization of the Ricci flow equation, okay? And if you're interested in the Ricci flow as a PDE, well, you'd like to understand solutions to the PDE, not the solutions to a regularization of it. You can also interpret this, Perelman's conjecture is asserting the existence and uniqueness of some sort of generalized solution to the Ricci flow equation. And a further motivation is that, right, if you want to apply Ricci flow to a family of Riemannian metrics, not just one metric, which is what we're going to be doing, well, then you kind of need a canonical process, and it should depend nicely on the initial data. Okay. Okay. So first we worked with John Lott and then Richard Bemler. So we proved this conjecture of Perelman. So that involved some pieces here. So first, there was a definition of the Ricci flow through singularities, which was new. And then we proved existence, uniqueness, and this convergence statement that Perelman indicated, and also continuous dependence on the initial condition. All right. So I want to describe this a little bit in a very condensed form. So first, there's the matter of the definition. So what is a Ricci flow through singularities? So the first idea is a very simple one, of just to work with some kind of space-time definition. So to motivate this, let's start with the conventional Ricci flow. So we have Ricci flow here, defined in a time interval from 0 to t. You can do a completely straightforward, completely obvious thing. We create a space-time structure. So the space-time will just be the product of the manifold with the time interval. Okay. Then you have a time function. which is just the projection onto the interval factor. And then you have a time vector field, which corresponds to the coordinate vector field on the interval factor. And then, right, so every time t, you can take the metric gt and put that on the slice m cross the singleton t. Okay, so you have what you get, in other words, is you get a Riemannian metric on the foliation defined by the time slices of this function. And then that Riemannian metric will satisfy the Ricci flow equation in this sense that its Lie derivative with respect to this time vector field will be equal to minus twice Ricci. Okay, so this is completely trivial construction, but then it leads to the notion of a Ricci flow spacetime. So that's just a four tuple where M is going to be a smooth four manifold with boundary. T is a time function, so that's a real value function. There'll be a time vector field. When you apply that to the time function, you get one, but meaning if you take a trajectory of the time vector field, then time increases at rate one. Okay. And then G will be a Riemannian metric defined on the level sets, the foliation defined by the level sets of time. And as before, G satisfies this Ricci flow equation. Okay. So this structure is this locally, it's exactly the same as what we had in the previous slide. You just look at a flow box, you can see it's the same thing. However, globally, it could look very different. Okay, it could be very far from being a product. So this allows for the possibility that the topology can change. Okay, so so now let me a little notation. So M sub t will just be the t level set of this time function, and I'll just use M as a shorthand for this whole tuple. Okay, so this notion of a Ricci flow spacetime is basically useless by itself. You have to impose some kind of restrictions. Okay, and the two restrictions that we use are what we call zero completeness and the canonical neighborhood assumption. Okay, so let me look at this cartoon again, right? So here you start at time zero, you flow upward, a neck pinch starts to form, and then you pinch, and this is, say, a singular time here, a singular time slice. So that's going to be, here in the picture, you see kind of two connected components, and actually, if you look at the distance from a point in this component, sort of to the singularity, so to speak, it's finite, okay? So you'd actually have, in this time slice, you could have a Cauchy sequence which has no limit, okay? And that's just built into the situation. You have to allow for this kind of phenomenon. Also, if you take a point on the initial time slice and you follow time trajectory forward, if you pick the point properly, it will go right into the singularity, okay? So that's that time, that trajectory is also incomplete for the time vector field. Okay, so this is part of the setup. So we have an adaptation, a replacement for the modification of the completeness notion, which is what we call zero completeness. Basically says incompleteness can happen, but if you stay in the part with controlled curvature, it won't happen. Okay, so formally, suppose you have a curve gamma in the space-time. So it's defined in a half-open time interval. Gosh, it's defined in a half-open time interval from 0 to S0. And so it should either be an integral curve of the time vector field, or it should be a unit speed curve in a time slice. Okay. So and the condition is if for this curve gamma, if the supremum of the curvature is finite, so it remains bounded along this curve, well then it has a limit at the right endpoint. Okay. So that's the completeness assumption. And then there's a notion of the canonical neighborhood assumption. This comes from Perelman's work. And basically that says when the curvature is large, the geometry of the flow is modeled by a standard solution, okay? Standard kind of solution, these are called kappa solutions. And examples would be shrinking round spherical space forms or shrinking round cylinders. So here, when the curvature starts to get big, the flow locally looks very much like a round cylinder. Here and here, when the curvature is getting big, it starts to look very much like a shrinking round spherical space form. And say here, after the neck pinch occurs, you have these kind of fingertip regions, which are going to be modeled on this this Bryant solitone. Okay. Anyway, so a singular Ricci flow. These are our basic objects. These are going to be. This will be a Ricci flow spacetime, which satisfies these three additional conditions. First, the initial time slice should be compact. So you're starting from a compact Riemannian manifold. And then these two other conditions hold: zero completeness and the canonical neighborhood assumption. Okay. Okay. So then we showed, right? So with John, we showed that if you take a compact Riemannian manifold XH, so then there exists a singular Ricci flow whose initial condition is isometric to that. So you have, for any initial condition, you get a singular Ricci flow. And then you have uniqueness, right? So if you have two singular Ricci flows and an isometry between the initial time slices, that can be extended to an isometry between the entire structures, okay? And I don't want to say what this means precisely, but we also show in an appropriate sense that, that the solution depends continuously on the initial data and proved Perelman's convergence conjecture, okay? So, okay, so a little bit more about what these things actually look like. So if you look at the part of a time slice where the curvature is large, so that's the region where this canonical neighborhood assumption holds, and following Perelman, you can show that these parts of the flow have very simple geometry and topology, right? So here, when the curvature starts getting big, you're entering an end of the manifold, which is diffeomorphic to S2 cross the non-negative rails. Here, when the curvature is large, well, you're just seeing a spherical space form, and so on. Also, the connected components of time slices, those do not have to be compact, but they're almost compact. Connected components are diffeomorphic to compact manifolds with finitely many points removed. So, for example, in this time slice here, you see two connected components. Each of them is a compact manifold with a single puncture. Okay, I mean diffeomorphic to a compact manifold with a puncture. Now, just as a remark, as far as we know, well, conjecturally this doesn't happen, time slices could have infinitely many connected components. And also, as far as we know, there could be uncountably many times where the time slice is non-compact. Okay? So, all right. So now let's come back to the topological questions that we started with. So how can you use an object like this to solve the deformation problems that we were looking at before, right? In the two-dimensional case, well, you run Ricci flow, it produces a metric with constant curvature, you're done, okay? Here you have some sort of horrible mess, right? So what do? So there are two approaches. One I would call removable singularities, and the other uses some kind of structure that we call partial homotopies, which is a little difficult to explain in a limited amount of time. So I'm going to focus on the first method, okay? So, so for this, let's say X is a spherical space form, but not the 3-sphere and not RP3, okay? And let's say GX will be some curvature 1 metric on X, all right? And now let's look at a G as a metric, an arbitrary metric on this space form, and M will be the singular Ricci flow with that as initial data, okay? So here, okay, so topologically, things are fairly simple. So at every time, okay, at most one connected component of that time slice MT will be diffeomorphic to X, the manifold we started with, possibly with finitely many punctures, okay? All the other components are topologically trivial. They're 3-sphere with finitely many punctures, each of them, okay? So we already saw that. So here you'll see, okay, my X has become M, but right, so here you see the original manifold punctured at one point, for example, and over here you see the 3-sphere punctured at one point, okay? You have extinction, so for some time, capital T, the times, after some time, the time slices are empty, okay? And then, okay, so since, because you have this extinction, right, there will be a supremal time where you see non-trivial topology, okay? So I'll call this omega G, so it's a supremal time for which the time T slice has a topologically non-trivial component, okay? And so the key fact here is that as you approach this time omega G from below, then in fact the time T slice will have a unique component CT, which is diffeomorphic to the manifold you started with. It'll have a unique component diffeomorphic to X, and that's not X with finite many punctures, it's just X itself, okay? And moreover, this component will become asymptotically round as you approach that time omega G, okay? So in the picture, so here, right, you go forward, the neck pinch happens, whatever, but over here, you follow the topology, eventually it will settle down. When that topology disappears, just before it disappears, you see this asymptotically rounded metric occurring, okay? So let's compare this with the situation in dimension 2. In dimension 2, you just see a metric with constant curvature arising as a limit from the Ricci flow. Here you see that, but it's somehow just showing up in this part of space-time, right? There's all this other garbage. Right? So the problem is you have this asymptotically round metric showing up here, whereas you want to get an asymptotically round metric on the manifold itself at the initial time slice, okay? So the idea is we just want to push that forward. We want to follow backward along trajectories of the time vector field and try to push that metric to the time zero slice, okay? So here we have a theorem which says that that almost always works. So if you have a singular Ricci flow and you take a connected component Z of some time slice, okay, well then there's a finite subset of that component so that every other point can be, you can flow all the way back to time zero, okay? So what I'm saying is, so let's say we're interested in this, the geometry here, you pick this slice, you try to flow it backward to time zero slice, you can do it as long as you avoid finitely many exceptional points, okay? And to understand what's going on, look at what's happening on this part of the space-time. So here, say in the cartoon, right, you see a neck pinch happening. Just after that neck pinch, you'll see this sort of fingertip that's rounding off, okay? Now, if you choose the wrong point on that fingertip and now run backward in time towards the singular time, it will go singular. It will track that fingertip as it goes singular, right? You can't use such a point. But the claim is there are only finitely many such points. Everybody else, you can push all the way back to the time zero slice. And when you do that, you can just simply push forward this asymptotically round metric, and you end up seeing that on the time zero slice, okay? So here, so you can push that forward to the time zero slice, and you end up with a canonical metric with curvature 1 that's associated with the original metric. There's some bad news, right? Nobody said that the image of that diffeomorphism is the whole initial manifold. So what you get is a metric with curvature 1. It's canonical, but it's only defined on some open subset, okay? And this guy is actually isometric to the standard metric on X with finitely many punctures, okay? So, and there's you get some appropriate continuous dependence of this structure on the metric G, okay? So the short version of what's left, a few minutes left, but the short version is we can use this result together with Hack's result for the 3-sphere to prove the generalized Snell conjecture, okay? So let me say a little bit more about this, right? So, right, so we have these assumptions here as before. Right, this is the fixed curvature 1 metric. We want to show that the space of curvature 1 metrics is contractible, right? So let's say for some m, we want to show pi m, the mth homotopy group is trivial, okay? So let's give ourselves now an m sphere of curvature 1 metrics on this manifold X, and we're trying to extend that to an m+1 disk, okay? Now, well, we have a map into the curvature 1 metrics that sits inside the space of all metrics, which is contractible, okay? So we can extend this to a map G from the m+1 disk into the space of arbitrary metrics, right? And therefore, for every point in the m+1 disk, right, we get an arbitrary metric, and then we look at this canonical partially defined metric, okay? So it's what I was talking about here, which is now you get this W sub G of P and G check of P, which is depending on the point P, okay? The bad news is these metrics are only partially defined, okay? So what we'll do is use this structure and we'll extend the metrics to constant curvature metrics. And to get the idea, let's, just to get warmed up, let's start with a single partially defined metric, okay? So just take a single partially defined metric. This is going to be, remember, this is isometric, although this is going to be isometric to the model metric, punctured finite set. Okay, so the picture is as follows. So here's our nice curvature one metric, right? And but then sorry, that's a background X, and then we have this open subset which could be quite horrible, right? And on that we have this curvature one metric, right? You have the complement is a closed set with finitely many connected components. Those correspond to the ends of W, right? Which correspond to the punctures that we removed, okay? So that means that if you look near, so if in this blue region here, you think about this curvature one metric, the near there, what you will be seeing metrically is a puncture, the neighborhood of a puncture in the model space, okay? So you'll see spheres, small spheres that go around those punctures, and topologically, those will surround these components, okay? So you see, say a sphere surrounding each of these components, right? And now we want to extend this curvature one metric across each of these nasty sets, right? So what do? Well, you have the sphere here, two sphere here. You take a neighborhood of that has a curvature one metric on it. That metrically, it looks almost like a tiny round two sphere. So of course, you can isometrically embed that into the three sphere, right? And so that will give you a map of the neighborhood of this two sphere into the standard three sphere. By Schoenflies, you can fill that in. You can map the three disk in. You can extend it to an embedding of the three disk into the three sphere, right? But now just pull back the metric from the three sphere, right? Pull back the metric from the three sphere, and that will give you a metric with curvature one on that three disk, okay? So we've extended the metric, okay? So the punchline here is, this extension to the diffeomorphism was not unique, right? But it's unique up to precomposition by a diffeomorphism of the three disks fixing the boundary, which is exactly the thing that Hatcher showed was contractible, okay? So morally speaking, I'm being a little bit fuzzy here, but morally speaking, that gives you an extension which is unique up to contractible ambiguity, okay? And so then you can use this in a kind of an obstruction theory argument too. Yeah. Okay, this argument, we don't want to be circular. Okay, this is not the argument used for reproving Smale. It's the other one involving partial homotopies, which I didn't talk about. Okay, but this argument works for spherical space forms. It also works uniformly for hyperbolic free manifolds, and also works for nil. It's basically what I described here. The last step is some sort of obstruction theory type argument. Yeah, so I think I'll stop there.
For the wonderful talk, do we have any questions?
Thank you for the wonderful talk and results. In oral communication, Perelman conjectured that for the canonical solution, the smooth part might even be analytic in time beyond the singular times.
Yeah, there's a corresponding statement for mean curvature flow, which seems even more, should be more tractable. Yeah, I don't know anybody's looked at that. Yeah, it's a great
but it's no counter. It could still be true, right?
Yeah, it could still be true. But I mean, as I said, like right now, as far as we know, so coming back to this cartoon, right? As far as we know, there could be uncountably many time slices which are non-compact. We do have an estimate that Hausdorff dimension at those exceptional times is at most 1/2. Okay, but I mean, I guess everybody conjectures that it's maybe even finite. Yeah. So yeah, there's a lot that one could try to establish from an analytical point of view.
We have other questions?
So the results you stated, you mentioned this at the beginning of the talk, in the topology of diff, it's independent of regularities, C1, C2, and so on. I mean, presumably your method, what is known about homeomorphisms when you go to MC0?
So
these methods maybe
let's see. So in dimension 3, the categories are the same. So I think there you could give an approximation argument. Yeah, it's, sorry.
You mean it follows from density of lithios and homeos?
Actually, I'm being a bit hasty there. you could probably, I think you could probably, so what is it, du Mois or something, the
Yeah.
fact that top is the same as diff in dimension 3, you could
Right.
probably track his proof through the families. You could try to do that. Yeah.
So then, okay, that's good, thanks.
Other questions?
It's not a question, but I've seen Perelman in your work. Is it the Russian mathematician who refused the field medals?
Yes,
Okay.
the same.
Thank you very much. Mm.
Thanks for your question.
Actually, I have a question. So in higher dimensions, and you mentioned it's very like difficult. Do you have any like insight from Ricci flow point of view, like maybe
Well,
why?
there's sort of the broad narrative that mentions things are flexible, low dimensions geometry plays a role. So that, I mean, I don't see, I mean, there's been huge progress in the last 5 or so years about diffeomorphisms in high dimensions, but it's using kind of conventional geometric topological techniques plus some kind of amazing advances by Galatius and Randall Williams and homological stability. So, I mean, it's a beautiful story, which I don't understand. So I guess I shouldn't say it's beautiful, but it seems to be beautiful, very impressive. But yeah, I mean, I don't think Ricci flow or geometric PDEs would have much to say about it.
Do we have other questions? If not, let's thank the speaker again. We will come back around 2:15 for the next talk.